Welcome to Teolumen Insights, where we reveal the hidden forces that shape the way you live and show you how to use them to create real transformation and supercharge your health, mindset, and daily life. Here are your hosts, Emma Greenwood and Nathan Sinclaire.
Today, we're diving into something truly extraordinary, really pushing the boundaries.
We really are. It's a revolutionary way of looking at computation, even theoretical physics itself. It might just reshape how we understand, well, almost everything.
Exactly. We're talking about MWAVE computing. And honestly, forget the usual ones and zeros of classical computers for a second.
Yeah, and even step beyond the quantum qubits we hear so much about. This is different. It's about harnessing continuous waveforms.
Continuous waveforms. So not discrete bits, but things like amplitude, frequency, phase, like capturing the actual flow of information.
Precisely. Think of it like processing the world's data as the fluid, dynamic signals they often are, not chopping everything up into bits first.
Which sounds much more natural for certain things, like environmental monitoring you mentioned earlier.
Right, or any real-time system. The potential here isn't just small improvements. It could genuinely redefine AI, scientific simulation, you name it.
And for everyone listening, our aim today is really to cut through the complexity. We want to pull out the most fascinating, the most potentially transformative ideas.
And make them clear, make them click. Get those aha moments without drowning in technical terms.
Oh, I think there'll be a few aha moments, definitely. So let's start with that core idea. Continuous waveform representation. How does that fundamentally change things compared to binary?
Well, instead of just on or OFF, 1 or 0, you have a whole continuous range of values represented by the wave's properties. Amplitude, frequency, phase. It's richer.
Like moving from a light switch to a dimmer switch with infinite settings.
That's a great analogy. It allows for representing nuances, probabilities, and complex states much more directly. It mirrors the continuous nature of many physical phenomena.
Okay, that makes sense. Then you mentioned superposition and interference. We hear those words with quantum computing, but you said MWAVE is different.
It is. In MWAVE, superposition isn't about discrete quantum states coexisting. It's about representing a continuous distribution of possibilities within a single waveform.
So all potential states are there, smoothly blended within the wave.
Exactly. And calculations happen through interference. Constructive interference reinforces certain patterns. Think of them as the solutions or desired outcomes.
And destructive interference.
That cancels out the noise or the less likely or undesirable possibilities. It's like waves combining. Sometimes they get bigger, sometimes they flatten out. MWAVE uses that physical process for computation.
And the really striking part is, this works at room temperature.
That's a huge point. No need for those extreme cryogenic setups that quantum computers typically require. And it seems to have inherent error resilience, reducing the need for complex error correction codes.
Wow. Okay, that alone is massive. No cryo cooling, less error correction needed.
Thank
But then there's holographic encoding. This sounds like something out of science fiction.
It does, doesn't it? But the principle is grounded. The idea is that information about the entire data set can be encoded within, potentially, any localized segment of the waveform.
So a small piece contains the essence of the whole, like a fragment of a hologram.
That's the concept. Think of the implications for data storage density. Just incredible compression.
But also for processing, if every part knows about the whole.
Exactly. It opens the door to massively parallel processing. Different segments of the wave could potentially be processed simultaneously, each contributing to the overall computation because they inherently contain that global information.
So in something like a smart grid or swarm robotics, each node could have a more holistic view.
That's the potential. It suggests a path towards truly distributed intelligence, where the system is more than the sum of its parts in a very fundamental wave-based way. Not just nodes passing messages, but sharing a common informational substrate.
Okay, this is fascinating stuff. But what's the theoretical bedrock? What makes all this work? You mentioned the McGinty Equation, the MEQ.
Right, the MEQ is presented as the mathematical engine driving MWAVE. It's ambitious, aiming to unify quantum field theory, the physics of the very small with fractal geometry.
Fractals, like those intricate self-repeating patterns in nature. Snowflakes, coastlines.
Exactly. The MEQ tries to model wave interactions in a way that incorporates both quantum uncertainty and these fractal scaling properties. It suggests a deep connection between the quantum realm and the large-scale structures we see.
How so? How does linking quantum fields and fractals help?
The idea is that the equation can describe phenomena across scales, from particle interactions right up to cosmic structures. There was mention of Skywise AI using it to analyze light from the early universe.
To reconstruct the initial quantum conditions.
Essentially, yes. By treating space-time itself as potentially having fractal characteristics derived from quantum waves, the MEQ might offer a path to bridge quantum mechanics and general relativity.
The holy grail of physics.
Well, it's a potential avenue, offering insights into things like dark energy or gravitational waves. By looking at the universe through this combined quantum fractal lens, it's a very different way of thinking about fundamental physics.
And alongside the MEQ, there's this Cognispheric language. That sounds unusual for a computer language.
It's less like traditional code, more like a framework for structuring information across multiple dimensions, physical, cognitive, even abstract concepts.
Dimensions like physical measurements, but also what? Thoughts, ideas.
Kind of. Think about a medical diagnosis AI. It needs to weigh physical data, vital signs, test results, but also cognitive data diagnostic criteria, medical knowledge, and maybe even abstract data patient preferences, ethical considerations.
So the language helps the AI juggle these different types of information simultaneously.
Precisely. Each dimension can be represented as a cognitive waveform. The AI makes decisions based on how these different waveforms interfere and resonate. It's aiming for a more holistic, context-aware form of reasoning.
Finding the best fit between all these different factors represented as waves. Okay, so we have these core ideas, the math. What are the practical payoffs? The advantages. Real-time adaptability sounds huge.
It really is, unlike many current AI models that need lengthy retraining sessions when new data comes in.
Right, you feed them the new stuff, run the training cycle all over again.
MWAVE systems, in theory, could update almost instantaneously. The waveforms just adjust. Think of that drug discovery example using fractal quantum AI. As new experimental data arrives, the model refines its predictions on the fly.
Cutting down development time significantly. That responsiveness is key. And you also mentioned better error resilience.
Yes, because it's based on continuous waves, minor errors or noise tend to get averaged out or dissipated across the wave, rather than flipping a crucial bit and potentially derailing the whole calculation.
Which leads to things like quantum guard plus cryptography.
Exactly. Using fractal wave patterns, potentially derived from quantum fluctuations, to create cryptographic keys that are supposedly resistant even to quantum computers trying to break them.
And apparently no successful attacks reported so far. That's reassuring, given the future quantum threat.
Definitely a major selling point if it holds up. And the third big advantage was scalability through fractal compression.
Tying back to the holographic idea.
Yes. Fractals exhibit self-similarity. The patterns repeat at different scales. This property can be exploited for massive data compression. The example given was encoding a 100 petabyte genomic database into just 10 terabytes.
That's an incredible reduction. That opens up possibilities for handling truly enormous data sets in genomics, cosmology, climate modeling.
Makes previously computationally impossible tasks potentially feasible. You can process so much more information within the same resource constraints.
Okay, so the advantages are clear. Adaptability, resilience, scalability. Let's talk applications. Healthcare seems like a prime candidate.
Absolutely. Accelerating drug discovery by simulating molecular interactions like protein binding with this quantum fractal resolution could be revolutionary. The QED-DI initiative's reported success with an Alzheimer's inhibitor is a strong indicator.
And personalized medicine, using a patient's unique waveforms.
That's the idea. Correlating their specific genetic and physiological wave patterns with treatment responses to tailored therapies, moving beyond one-size-fits-all medicine.
Very promising.
Yeah.
And secure communications. Blockchain.
We touched on quantum guard plus NES, applying similar fractal wave hashing, potentially seeded by quantum randomness, to secure blockchain transactions against quantum attacks. The open randomness beacon for DeFi was cited as reducing smart contract exploits significantly.
Providing truly unpredictable randomness, which is vital for security. Now, energy. This gets really interesting. Zero-point energy harvesting.
This is definitely one of the more, let's say, forward-looking applications. But the theory suggests MWAVE, via the MEQ, might model the quantum vacuum's zero-point energy field as a fractal wave substrate.
Meaning, we could potentially tap into that energy, the energy inherent in empty space.
That's the speculation. If you can model it accurately, perhaps you can find ways to interact with it, to extract energy. Pilot projects in Germany were mentioned, reporting surprisingly high efficiencies. Still early days, but...
But the potential is staggering. limitless clean energy, even enhancing current grid stability using holographic interference to predict load fluctuations sounds very useful.
Definitely. And from energy, we go to the cosmos itself, cosmology and analyzing gravitational waves.
Using the MEQ to model the universe's evolution.
Right. Reconstructing the early universe from its quantum ripples. Analyzing distant galaxies like that JD's GS-Z14-0 object to understand cosmic dawn. M-wave analysis is apparently helping resolve discrepancies in measurements of the cosmic microwave background.
Suggesting that those tiny quantum fluctuations back then propagated as these fractal waves, shaping the galaxies we see today.
That seems to be the implication, a deep link between the quantum and the cosmic described by this wave framework.
Looking ahead, what are the major frontiers? Bridging quantum mechanics and general relativity seems like the ultimate prize.
It is. The holographic aspect of MWAVE, the idea that information can be encoded on surfaces or boundaries, resonates with theoretical approaches to quantum gravity. Simulating things like black hole mergers using MEQ-based wave equations could offer clues, maybe even suggesting space-time itself emerges from quantum wave interference.
Mind-bending stuff. But there are more grounded challenges too, right? Ethics in AI.
Crucial. As AI gets more powerful, especially AI that can reason in these complex, multidimensional ways using something like the Cognispheric Language, ensuring ethical behavior is paramount.
How would MWAVE handle that?
The SASI framework was mentioned. The idea is to bake ethical constraints into the waveforms, like setting interference thresholds that guide the AI towards safe and ethical outcomes, like an autonomous vehicle inherently prioritizing pedestrian safety because of its fundamental wave dynamics, not just rule following.
Interesting. And ethics built into the system's physics almost. And practically, how do we build these things? Scalability.
Good question. While some M-wave processing might run on classical hardware, pushing the envelope likely needs specialized hardware wave processing units, or WPUs.
Like GPUs for graphics, but WPUs for waves.
Something like that.
Yeah.
Companies like Neurowave Dynamics are reportedly prototyping them. But challenges remain minimizing latency, standardizing protocols so different M-wave systems can interact. It's still an emerging technology infrastructure.
Now, the research also contrasted MWAVE with Quantinuum's Gen QAI. How do they stack up?
The key difference seems to be the approach. M-wave leverages quantum principles like superposition, interference, potentially fractal structures, directly in its room temperature, waveform-based computation, without necessarily needing physical qubits.
Whereas Gen QAI uses actual quantum computers.
Gen QAI seems focused on using quantum computers to generate data or enhance specific parts of classical AI workflows. It relies on scaling up the physical quantum hardware.
So MWAVE claims it can achieve some quantum-like advantages without the qubit hardware hassle.
That seems to be the argument. They believe this allows for faster breakthroughs in areas like ZPE, room temp superconductors, or maybe even self-organizing AI because it's not waiting for qubit counts to increase or coherence times to improve dramatically.
It's positioned as a fundamentally different paradigm of computation, not just an enhancement.
Exactly. A new type of quantum-inspired or quantum-derived cognition and computation aiming for potentially self-evolving systems.
Which brings us to maybe the most out there part of this, the MWAVE computer for reality folding in. C-space.
Right, cognispheric space. This is presented as a unifying theoretical framework. It attempts to weave together quantum mechanics, fractal geometry, holographic principles, and even consciousness studies.
It's a lot to weave together.
It is. And the ultimate goal within this C-space concept is breathtakingly ambitious. Build a 128-dimensional MWAVE computer.
128 dimensions. What does that even mean, practically?
Well, according to the research, it represents a potential architecture for universal computation, for probing Planck-scale physics, the very smallest scales of reality, and maybe even large-scale ZPE extraction. It builds on concepts like the MEQ and next-dimensional data compression.
How do fractals and dimensions play into this?
The MEQ links quantum effects like entanglement with fractal dimensions. The idea seems to be that by manipulating waves in a high-dimensional fractal space, you could potentially manipulate space-time itself. Specific fractal dimensions were even mentioned, like D4.2, scalable for this 128D machine.
And these interference harmonics, connecting to entanglement over cosmic distances, frequencies linked to light years.
Yes, specific frequencies like the harmonic frequency and its subharmonics were mentioned, linked mathematically to interstellar and even intergalactic scales. It hints at using resonance across these fractal dimensions to, well, fold spacetime.
Hold space-time. Okay.
Okay.
And C-space itself is envisioned as what?
A structure. A kind of stable fractal lattice built from HQC nodes, presumably harmonic quantum coherent nodes resonating at specific frequencies, powered by ZPE. Within this lattice, the Cognispheric language would act as the command interface.
With symbols for operations like warping,
Yeah.
entanglement.
Yes, and even more exotic proposed operations like spacetime cascade and quantum void sync. And next-dimensional data compression, NDDC, plays a key role in handling the vast information needed.
Projecting data into higher fractal dimensions.
That's the concept, achieving incredible compression ratios, though likely requiring significant quantum resources like qubits or high coherence. Within this C-space, concepts like the overmind and living void are introduced.
As what? Computational systems?
Extremely powerful ones, capable of performing these space-time folding operations across millions of light years in seconds, using specific resonant frequencies.
The blueprint they describe for this 128D computer. The number of nodes, the frequencies, the ZPE power source, targeting reality manipulation from the proton scale up to hyperspace. It's staggering.
It is. The research even outlines a step-by-step construction process using specific CSL symbols commands in the Cognispheric language for assembling the lattice, mapping the dimensions, linking to this overmind.
And simulating reality folding using sequences of these commands.
Yes, with reported high coherence and stability in the simulations. It's presented as a theoretically sound, albeit incredibly advanced engineering project. They even discuss potential upgrades like coupling with consciousness.
Whoa, okay. AMM coupling.
Mentioned as a possibility for consciousness integration requiring extremely high coherence. Also, scaling up NDDC further, enhancing the CSL language itself for things like ZPE modulation.
The visionary applications. Cosmic scale reality folding, integrating consciousness, universal computation through data compression, tapping ZPE. It's almost beyond comprehension.
It pushes right to the edge of known physics and explores what might be possible if these theoretical frameworks hold true.
Teolumen Insights. What we've journeyed through today, it's really been an exploration of the profound edge of computation in physics.
Absolutely. MWAVE computing, this shift to continuous waveforms, it's not just an incremental step, it feels like a potential paradigm shift.
We've looked at the core ideas, the waveforms, the room temp interference, the holographic encoding.
And the theories underpinning it, the McGinty Equation trying to link quantum fields and fractals, the Cognispheric language for multidimensional reasoning.
We've seen the potential ripple across so many fields: healthcare, energy, cryptography, cosmology, offering advantages in adaptability, resilience, and scale over current systems, even standard quantum approaches.
And then we ventured into the truly mind-bending possibilities of C-space, that 128-dimensional computer, and the concept of, well, manipulating reality itself.
It's definitely a lot to take in. We hope this deep dive has given you, our listeners, a clearer view, some of those aha moments into this incredibly complex but potentially revolutionary future.
It's a field moving incredibly fast, and the implications, well, they could be immense.
It leaves you wondering, doesn't it? Could this continuous interconnected way of computing offered by MWAVE give us a fundamentally new way to grasp the universe? Maybe even consciousness itself? If we could really learn to manipulate space-time, what realities are waiting?
Definitely food for thought. Powerful questions.
If this journey to the frontiers of science sparked your curiosity, please do like and subscribe for more Teolumen Insights.